Hello everyone, my name is Radu Horoiu. I'm a professional services engineer at Infinet Wireless. Thank you very much for joining our webinar. Today we will discuss about the enhanced quality of service features of the Infinet Wireless devices. The agenda includes 3 items. We will begin with an overview of QoS, pointing out its main mechanisms and parameters. Then we will see what are the advanced QoS capabilities of the Infinet Wireless devices. And in the end, I will show you how to configure the QoS parameters on the Infinet Wireless units in a test scenario that I have prepared in our lab. As you probably know, the QoS term stands for quality of service, and it describes the overall performance of a network, especially in terms of the service quality perceived by the user. At the most basic level, the network service quality is evaluated by 3 parameters. The first parameter is loss, which represents the number of transmitted packets that are not received at the destination due to network congestion, for instance. The second parameter is delay or latency, which represents the amount of time a packet travels between the sending and the receiving endpoints. And the third parameter is jitter, which represents the delay variation of the transmitted packets. For instance, if a packet requires 100 milliseconds to cross the network from the source endpoint to the destination endpoint, and the next packet requires 125 milliseconds to make the same trip, then the latency variation is 25 milliseconds. There are 3 known approaches regarding QoS implementation within today's data transfer networks. The first model is the best effort delivery, where there's no differentiation between the data streams, for example, the internet traffic. The second model is the differentiated services model, or diffserv, which works as follows. The network devices recognize the important packets, select them from the whole traffic, and then provide the appropriate services to them, which is like scheduling some cars on fast straight lanes on a paid highway and other cars on slow curved neighboring roads. And the third model is the integrated services model, or intserv. In this approach, the application should make reservations using the RSVP protocol in order to get preferential treatment throughout the whole network, similar to a speeding ambulance with sirens on that clears the path through the whole city. In case of the diffserv approach, which is the model used by the Infinet units, the main QoS mechanisms for traffic handling and bandwidth management are: first of all, classification. The traffic must be identified and separated into different flows or groups of flows. This requires a form of packet tagging or marking. The most common classification techniques are listed in the following table. So, at the application layer, traffic can be classified using user and application ID. At the transport layer, the classification can be done using a quintuple IP header that contains source and destination IPs, source and destination ports, and protocol. At the network layer, we have IPTOS, or type of service, which uses the IP precedence field within the IP packet header to create 8 types of IP service classes in order to identify or set different priorities. IPTOS was later redefined as DSCP, and the priority classes were extended from 8 to 64 by using 6 bits instead of 3. And at the data link layer, the COS, or class of service field within the layer 2 header, is used to set priorities. COS is available only when .1q tagging is in use, and it consists of a 3-bit priority field within the 4 bytes of the .1q tag. The next important QoS mechanism is packet scheduling, which involves deciding which packets from the transmission queues should be transmitted in a certain time interval. This is done using several queuing techniques such as first in, first out, priority queuing, custom queuing, weighted fair queuing, class-based weighted fair queuing, and strict priority queuing. Next, the congestion avoidance mechanism, prevents a queue from filling, allowing high-priority traffic to enter the queue. A method to accomplish this is traditional packet drop or tail drop, in which case if a queue is full, all the subsequent packets are dropped until the queue has enough space to accept more traffic. More advanced methods can be used to selectively decide which packets to be dropped when the queue limit is reached. Traffic shaping is another important QoS mechanism because it involves buffering the excess inbound packets and scheduling them for later transmission in order to ensure a constant throughput on the outbound interface. And last but not least, the link efficiency is essential in case of wireless networks. Techniques like packet compression can be used to transmit more data in the same amount of time, thus improving the overall service quality. Moving on to the QoS features offered by the Infinet Wireless devices. First of all, I want to mention that Infinet Wireless provides its customers with some of the most advanced QoS capabilities of all the broadband wireless solutions available today. The Infinet proprietary QoS techniques are close to the Ethernet QoS techniques. Using our units, it is possible to assign customized priorities using values in special frame and packet header fields according to the required type of service. Infinet Wireless uses the differentiated services approach in order to ensure the appropriate quality of service for the most diverse and demanding applications like voice, video, business applications like CRM, remote desktop connections, and so on. The OneFlex operating system is the mastermind of the Infinet Wireless R5000 devices. The inbound traffic, after being processed by several other modules, is forwarded to the QoM module, which manages all the quality of services parameters. Every data stream goes through the QoM module before the egress or after the ingress from or to any interface. Within the QoM module, the traffic can be classified, marked, prioritized, redirected, scheduled, or shaped. The first task of the QoS module is to differentiate between the traffic flows in order to prioritize them accordingly. So, in terms of traffic classification and priority assignment, the Infinet Wireless R5000 devices offer smart and flexible traffic filtering and classification up to layer 4 using any attributes including IPTOS, DSCP, .1p or Q tags, VLAN, IP, MAC address, protocols like TCP, UDP, ports, etc. Up to 32 physical queues, 17 of which are user configurable, so you can decide in which of these queues to put a certain traffic flow. The rest of 15 queues are system reserved. And up to 17 min priority levels for a granular traffic prioritization. They range from 0, which is the highest, to 16, which is the lowest priority. Each data stream will receive a min priority value. By default, if no rules are configured, or if no other priority tag is recognized, all traffic passing through the node is marked with min priority 15, which means best effort. The conversion table between min priorities and .1p, TOS, and DSCP priorities can be found in the product documentation at the web address that you can see on the screen. Of course, you can assign whichever priority you desire for every data stream that passes through the unit. You can even change the existing DSCP tags of the packets, for example. In the following animation, you will see how the Infinet QoM module assigns min priorities to incoming packets with different DSCP or COS tags. So, in the first example, a packet marked with DSCP48 enters the unit through the Ethernet interface, receives min priority 1, and then exits the device through the radio interface. The packet will have min priority 1 all across the Mint network if there is no rule defined by the user that changes this. Then, in the second example, a packet marked with COS priority 3 receives min priority 9. The scheduling techniques determine which packet from which queue will exit the device first based on the assigned priority. As mentioned earlier, Infinet units have 17 physical queues available for the user traffic in correspondence with the 17 min priority levels. The Infinet QoM module supports two scheduling algorithms. The first one is weighted fair queuing, which is enabled in the default configuration, and it uses weights for every queue of an interface, which allows for different queues to have different service shares depending on the weight value. The second scheduling technique is strict priority queuing. In this case, packets within the lower priority queues are not processed if the higher priority queues are not empty. In the next animation, you can see how the mint packets enter the queues based on the different priorities and exit according to weighted fair queuing or strict configuration. So when strict priority queuing is used, you can see that the lower priority packets are not allowed to exit the unit until the higher priority packets are processed. Traffic shaping means retaining the excess packets in a queue or buffering the delayed packets and scheduling the excess for later transmission. So the result is a smooth output packet rate. The Infinet Wireless R5000 devices use the concepts of classes and channels to organize the traffic. Up to 200 logical queues or QM channels can be created on a single device to facilitate a granular classification of any traffic type. And rules are used to direct certain traffic types to specific logical queues. The channels and classes can be organized in a hierarchical structure, as you can see in the picture, in order to allow bandwidth sharing between them. This enables the implementation of useful services such as oversubscription. In the following animation, you can see how the packets arrive at random speed at the Infinet unit. In contrast, the packets exit the unit in a uniform manner, ensuring a constant throughput. In the absence of traffic shaping techniques, the throughput would be fluctuating, making it difficult to maintain an optimal operation level for all applications. Infinet units benefit of the auto QoS implementation, so they can automatically prioritize the following traffic types: RTP packets, IPTOS, .1p tags, TCP acknowledgements, tunnels, PPPoE, and ICMP. RTP, .1p, and ICMP packet prioritization are enabled in the default configuration, but all the options can be enabled or disabled by the user. RTP detection can be easily monitored from the web interface. You must go to Device Status, click on RF50, and then choose General Statistics. In case there is RTP traffic passing through the link, the voice mode will be automatically changed to on. Moving on to the last item of today's session, during which I will show you how to configure QoS on the Infinet units. For this purpose, I have prepared the setup that you can see in the picture. So we have a simple point-to-multipoint topology with one base station and two CPEs. The base station is connected to the servers of an ISP, and the CPEs are each connected to two client PCs. The customer traffic is separated across the ISP network using different VLANs. The first two PCs are connected to CPE1 using a VLAN-capable switch in order to show the ability of the Infinet unit to change the VLAN tag of the traffic, while the last two PCs are connected to CPE2 directly using the two Ethernet ports of the unit. The total capacity for each CPE has to be limited at 20 megabits per second, which will be shared between the two PCs behind each CPE. Each of the four clients requires different service levels. So the traffic of PC1 needs a committed information rate of 12 megabits per second and min priority 2. The traffic of PC2 requires a CIR of 3 megabits per second and min priority 12. For PC3, the CIR must be set at 7 megabits per second with min priority 8. And for PC4, the required CIR is 1 megabit per second with min priority 15. The peak information rate must be set at 20 megabits per second for all PCs, so each client can benefit of the entire CPE capacity if there is no other traffic passing through the unit. QoS policies must be configured to split the base station bandwidth among the CPEs. Next, let's see how the base station QoS should be configured. First, the switch group configuration must be performed. Switch group 1 is used for the data traffic and should be set to the trunk operational mode in order to ease the configuration when multiple VLANs must be sent to several customers. Then switch group 100 is created for the management of the unit. In order to allow management only from the ISP server side, switch group 100 has only one port, Ethernet 0. Filtering rules must be configured for each switch group to allow only the required VLANs. After the switch group settings, the dynamic QoS configuration must be performed. Please note that in this example it can be done only via CLI because we must use hierarchical classes and their configuration cannot be performed using the web GUI. So, class 1 is used for CPE1. It has a maximum capacity of 20 megabits per second and it is the parent of class 2 and class 3. Class 2 is used for the traffic of PC1, which is tagged with VLAN 101. Channel 1 belongs to class 2 and it is used for the downlink traffic of PC1 from base station to CPE1. The add-out expression is used to define rules for the outbound traffic, and in case of the base station, outbound on the RF interface means downlink. Channel 2 also belongs to class 2 and it is used for the uplink traffic of PC1. The add expression is used to define rules for the inbound traffic, and in case of the base station, inbound on the RF interface means uplink. Class 3 is used for the traffic of PC2, which is tagged with VLAN 102. Channel 3 belongs to class 3 and it is used for the downlink traffic of PC2. And channel 4 also belongs to class 3 and it is used for the uplink traffic of PC2. In a similar way, classes 4 to 6 and channels 5 to 8 must be defined for the traffic of CPE2. Priorities are set for each channel according to the required service level. And the CL parameter is used to allow each channel to use up to the entire capacity of its parent class. The configuration of CPE1 starts with the switch groups as well. Switch groups 101 and 102 are used for the data traffic, and they should be set to the in-trunk operational mode with specific mentioning of the trunk group defined on the base station, which is trunk 1 in this case. Rules must be configured for each switch group to allow only the required VLANs to pass. In a usual scenario, you should configure the Ethernet and RF ports as pass in order to keep the VLAN tag and send the data as it was received in both directions. However, in this scenario, we intend to show that the unit is able to also change the VLAN tags, so the tag option is used for both ports. Switch group 100 is used for the management of the unit. In order to allow management only from the ISP servers, switch group 100 has only one port, RF50. This way, the unit cannot be accessed from the client side. The dynamic QoS configuration is similar with the one performed for CPE1 on the base station. In our example for the uplink and downlink traffic on VLAN 101, the minimum guaranteed capacity is 6 megabits per second, so the 12 megabits per second CIR of PC1 is split 50-50 between uplink and downlink. The maximum capacity is 20 megabits per second when there is no traffic in the other direction and in VLAN 102, and 10 megabits per second when in the other direction there are at least 10 megabits per second and there is no traffic on VLAN 102 because of the 50-50 uplink-downlink ratio. I will show you a bit later how this works during the tests. The situation is similar for the traffic in VLAN 102. The min priorities assigned at the channel level will determine the traffic to be placed in a corresponding queue, and according to the output criteria, the delay and jitter parameters will be affected. For CPE2, switch groups 103 and 104 are used for the data traffic and should be set to the in-trunk operational mode, similar to the CPE1 configuration. Because the two PCs that are connected to CPE2 use untagged traffic, no VLAN filtering rules can be configured on the switch groups. Since the Ethernet ports must be in access mode, the strip option must be configured for both Ethernet 0 and Ethernet 1. On the other hand, the RF interface should tag the traffic with VLAN 103 or VLAN 104, so it is set as tag on both data switch groups. And switch group 100 is used for the management of the CPE2 unit as well. The dynamic QoS configuration of CPE2 is similar with the one performed on the base station. For the uplink and downlink traffic on VLAN 103, the minimum guaranteed capacity is 3.5 megabits per second, so the 7 megabits per second CIR of PC3 is split 50-50 between uplink and downlink. The maximum capacity is 20 megabits per second when there is no traffic in the other direction and in VLAN 104. And 10 megabits per second when in the other direction there are at least 10 megabits per second and there is no traffic in VLAN 104 because of the 50-50 uplink-downlink ratio. The situation is similar for the VLAN 104 traffic. In the next few slides, I will show you how the previous configurations work by performing a series of tests. For the first test, I have generated two UDP streams of 30 megabits per second, so more than the capacity allocated per CPE, from the server towards PC1 and PC2 at the same time, using the following iperf commands. The result is that the 20 megabits per second of the class 1 of CPE1 are divided proportionally between PC1 and PC2 in accordance with the CIR and PIR values. So PC1 will get about 16 megabits per second, 4 more than the CIR value, and PC2 will get about 4 megabits per second, 1 more than the CIR value. It is important to note that only the CIR and PIR parameters influence capacity balancing, not the priorities. For instance, if the two streams from this example had the same CIR and PIR, the allocated capacity for each channel would have been the same, regardless of the priorities. However, the priorities still influence delay, jitter, and so on, and they also come into play when the base station capacity limit is reached or exceeded. For the second test, I have generated the same 30 megabits per second streams, this time from the server towards PC3 and PC4 simultaneously. You can see that the bandwidth distribution between PC3 and PC4 is different from the one of PC1 and PC2 because of the different CIR parameters. During the third test, I have generated one single stream of 30 megabits per second from the server towards PC2. The result is that since there is no traffic to or from PC1, PC2 gets the entire capacity of the class 1 of CPE1 thanks to the CL command. For the fourth test, two streams of 30 megabits per second have been generated at the same time, one from the server towards PC1 and one from PC1 towards the server, so in uplink and downlink simultaneously. You can see that since there is no traffic to or from PC2, the entire 20 megabits per second of class 1 of CPE1 is allocated to the PC1 traffic, and it is equally split between the uplink and downlink streams, because I have set the uplink-downlink ratio to 50%. Next, I have generated 8 simultaneous streams of 30 megabits per second, 4 from the servers towards PC1, 2, 3, and 4, and another 4 streams from PC1, 2, 3, and 4 towards the servers. So basically, all the computers in the setup were sending and receiving data at the same time. The result is that the traffic is limited according to the QoS settings performed earlier. So the VLAN 101 traffic gets about 16 megabits per second, 8 in uplink and 8 in the downlink direction. The VLAN 102 traffic is limited to a total of 4 megabits per second. In VLAN 103, the total bandwidth is about 18 megabits per second. And the VLAN 104 traffic is limited to about 2.6 megabits per second, also split 50-50 between uplink and downlink. And for the final test, first I have limited the capacity of the base station to about 15 megabits per second, and I have set the And for the final test, First, I have limited the capacity of the base station to about 15 megabits per second, and I have set the prioritization to strict using the following commands. So in my case, because I have used the 40 MHz bandwidth, I had to set the unit to the MISO mode and the bitrate to 15,000. Then I have generated two simultaneous streams of 30 megabits per second from the server to PC1 and PC2. And the result is that since there is not enough capacity for both streams, not even for one, and the strict prioritization is enabled, all the available capacity will be allocated to the highest priority stream, namely the VLAN 101 traffic. The QoS statistics tool on the radio interface of the base station can be used to view the incremented traffic queues according to the 4 priorities that were configured earlier. So you can see that the packet count for queues with mean priorities 2, 8, 12 and 15 has been incremented. This brings us to the end of today's presentation. Thank you once again for your time, and I hope to see you again during our next webinar.